Welcome back to Applied Physics Lecture Series, Unit 2, Semiconductor Physics, Lecture 6, Hall Effect and its Applications. So first of all, you have to know what is this Hall effect. So Hall is the name of the scientist who invented a new phenomena in a piece of metal or in a piece of a semiconductor. That's why it is known as Hall effect. Consider a current carrying conductor or semiconductor and assume in an x direction current is flowing. Then if you apply the magnetic field in a direction which is perpendicular to the current flowing direction, let us say in a z direction, as a result, as a consequence, an electric field will be developed in a direction which is perpendicular to both current flowing direction and magnetic field applied direction, that is along y direction. So this phenomena is known as Hall effect and the generated voltage is known as Hall voltage. So if you want to express in detail about this one, if we consider a piece of semiconductor or a metal carrying current is placed in a transverse magnetic field, an electric field is produced inside the conductor in a direction which is normal or perpendicular to both current flowing direction and magnetic field direction. This phenomena is known as Hall effect and so-called generated voltage is called as Hall voltage. If the material is a p-type semiconductor, because here we are having two types of extensive semiconductors. One is n-type semiconductor and the second one is p-type semiconductor. If we consider the material as p-type semiconductor, when electric and magnetic field is applied at right angles to each other, holes experience a force and those are accumulated on one face of the material. Because in case of p-type semiconductor, majority charge carriers are holes, that's why those are experience a force and they are accumulated on one face of the material. This causes a potential difference and a voltage which is developed called as Hall voltage. And if you consider the material that has n-type semiconductor, when electric and magnetic fields are applied at right angles to each other, electrons experiences a force and they are accumulated on one face of the material. This causes a potential difference and a voltage which is developed. Such a voltage is called as Hall voltage. In this diagram, you can able to notice all the three. Consider the blue one, that is a piece of a semiconductor in which current is flowing along the x direction, which is represented with I, and the current flowing direction is represented with green color. And if you apply the transverse magnetic field, that means a magnetic field which is perpendicular to the current flowing direction, for example, along z-axis, which is represented in red color. As a result of this one, an electric field will be generated which is perpendicular to both current flowing direction and magnetic field applied direction, so which is represented with the black color, and throughout the material a corresponding voltage is developed called as Hall voltage. Consider an n-type semiconductor in which electrons are moving with a velocity v to v, so as a result current flow will be noticed. Let B be the applied magnetic field which is applied perpendicular to the current flowing direction. The electrons will experience a force which is nothing but BeV due to the application of magnetic field. This causes the electron current to be deflected, causing a negative charge to accumulate on one face of the semiconductor. A potential difference is established across the two faces of the material, causing an electric field EH. Here it is called as Hall field. This field gives rise to a force of E into EH on the electrons. And at equilibrium, the force experienced by the electrons under electric and magnetic fields are equal. That's why E into H is equals to BeV. So from this, we will get the expression for Hall voltage EH is equals to BV, known as equation number 1. If you consider the current density as J, then J is equals to NeV, where N is the number of charge carriers. So from this expression, the velocity V is nothing but J by Ne, known as equation number 2. Substitute the value of velocity from equation 2 in equation 1 and we are rearranging the terms. Finally, we will get EH is equals to B into J by Ne. The Hall effect is described by means of a Hall coefficient which is represented with RH. The expression for RH is nothing but 1 by Ne if it is a n-type semiconductor, or RH is equals to 1 by Pe if it is a p-type semiconductor. You know EH is equals to B into J by Ne, or EH is equals to B, J or H. As a result, RH is equals to 1 by Ne, that equals to EH by Bj. EH is the Hall field or Hall voltage, B is nothing but magnetic field, J is nothing but current density. And what is the use of this Hall effect? By deriving the expression for Hall coefficient. So based on that Hall coefficient, we are having very few important applications. Out of those, The important applications are, few important applications are, the first one is to determine the type of a semiconductor. The Hall coefficient RH is negative for N-type semiconductor and it is positive for P-type semiconductor. That means without testing the semiconductor which is given to you, you can able to identify the type of a semiconductor, whether it is an N-type semiconductor or P-type semiconductor, by observing the sign on the semiconducting material. If the sign on the sign of the Hall coefficient on the semiconducting material is positive, then it is a P-type semiconductor. Or the sign of the Hall coefficient which is present on the given semiconductor is negative, then it will be an N-type semiconductor. In this way, without testing the semiconducting material, you can able to identify the type of semiconducting material based on the sign of Hall coefficient. And the second important application is calculation of carrier concentration. That means you can able to find out majority charge carriers in N-type semiconductor or P-type semiconductor, respectively those are electrons and holes. If RH is equals to 1 by Ne, from that expression N is equals to 1 by E into RH. Here E is nothing but charge of the charge carrier and RH is nothing but Hall coefficient. Here N is number of charge carriers. If you know the values of charge of the charge carrier and Hall coefficient, very easily you can able to find out carrier concentration. And the next important application is determination of mobility. You know, the mobility is very, very important. Mobility is nothing but transportation. Don't it is conduction in any type of material. How to notice, how to observe, or how to consider the transportation phenomena, which is nothing but mobility. If the conduction is due to electrons, then the conductivity can be written as sigma is equals to Ne mu. Here mu is equals to sigma Ne, that is equals to sigma into RH. Here sigma is the expression for conductivity. Mu is the mobility of the charge carriers and N is the number of electrons and E is their effective charge. Therefore, finally, the mobility expression mu is equals to sigma into RH. So with this, by knowing the conductivity and Hall coefficient of a material, we can able to find out the mobility. And the next important application of Hall coefficient or Hall effect is measurement of magnetic flux density. Hall voltage is proportional to the magnetic flux density for a given current. That means if you make the current as constant and then you are applying the magnetic field, that means how much amount, how much magnitude of magnetic field you are going to apply, exactly the same magnitude of Hall voltage is generated. Therefore, how much amount of Hall voltage is generated, that is exactly proportional to the magnetic field that you are applied. So Hall effect can be used to measure the magnetic flux density in a material. Thanks for watching.